Let's do the questions. A source emits 45 joule of energy in 15 seconds. So we need to find the radiant flux. So this is the first one. We know that radiant flux is equal to total energy, radiant flux equal to total energy emitted over time period. So it will be 45 over 15 seconds, which will give us 3 watts. So this will be the radiant flux, 3 watts. In the second question, we have a photographic plate which records sufficiently intense lines when it is exposed for 12 seconds to a source of 10 watt. How long should it be exposed to a 12 watt source radiating the light of same color to get equally intense lines? So this is our second one. So first of all, the formula will be like this: power into time equal to power into time, so that we get equal intensities. So simple, T will be 10 into 12 over 12, which will give us 10 seconds. In the third one, we have a figure. We need to find the relative luminosity of different wavelengths. So the graph is this one. This one. So from here you can see the wavelength, and you can easily see the value of relative luminosity. Okay, so you can easily do this part. For example, if it is asked from here, you can easily find, like if 500 is asked, then this will be the value for 500. If 600 is asked, this will be the value for 600. If 700 is asked, this will be the value. If 400 is asked, this will be the value. So you can find any value using the graph. In the fourth question, we have relative luminosity of wavelength 600 nanometer given, which is 0.6, and we need to find radiant flux of 600 nanometer light, which will produce same brightness sensation as produced by 120 watt of radiant flux at 555 nanometer. So this one is the fourth one. So what is the formula for relative luminosity? Relative luminosity, it will be equal to luminous flux of a source of given wavelength upon luminous flux of a source of 555 nanometer of same power. So 0.6 equal to luminous flux of source of, let's say, P watt or X watt over 685 P. So the luminous flux will be 685 P into 0.6, which will be 120 into 685. So P will be 120 over 0.6 equal to 200 watt. So this will be the value. In the fifth question, we have luminous flux of monochromatic source of 1 watt, and it is 450 lumen per watt. We need to find relative luminosity. Fifth one. So relative luminosity equals luminous flux of source of given wavelength over luminous flux of 555 nanometer source of same power, which is 450 over 685, which will give us 66%. In the sixth question, a source emits light of wavelength 555 and 600 nanometer. Radiant flux of both are given. Now, radiant flux of 555 nanometer part is 40 watt and for 600 it is 30 watt. We need to find relative luminosity at 600 nanometer. And sorry, it is given, it is 0.6. So we need to find total radiant flux and total luminous flux and luminous efficiency. So let's do the sixth one. What we have in the first part, we need to find total radiant flux. So it will be, total flux will be 40 watts plus 30 watts, that is 70 watts. Then luminous flux, it will be luminous flux of 555 nanometer and luminous flux of 600. So add them both, it will be 1 into 40 into 685 plus 0.6 into 30 into 685, which will give us 39730 lumen. Now the C part is luminous efficiency. So it is total luminous flux over power input. So 35 into 685 over 100, it is 239.75 lumen per watt. In the eighth question, source emits 31.4 watt of radiant flux distributed uniformly in all directions. Now luminous efficiency is 60 lumen per watt. We need to find luminous intensity of source. Eighth one. So radiant flux (31.4 watt). We know total solid angle is 4 pi because it is uniformly emitting in all directions. Therefore, we are taking the complete solid angle. Luminous efficiency is 60 lumen per watt. Luminous flux will be 60 luminous efficiency into radiant flux, that is 16 into 31.4 lumen. So luminous intensity will be luminous flux over power input over 4 pi, sorry, because it is in all direction. So 60 into 31.4 over 4 pi, which will give us 150 candela. Now let's do the seventh one. We left the seventh one. Light source emits monochromatic light of wavelength 555 nanometer. Source consumes 100 watt of electric power and emits 35 watt of radiant flux. So we need to calculate overall luminous efficiency. So in the seventh one, overall luminous efficiency will be equal to total luminous flux over power input. So it will be 35 into 685 over 100. So it will give us 239.75. lumen per watt. In the ninth question, a point source emits 628 lumen of luminous flux uniformly in all directions. It is placed at the origin, that is at 0, 0, 0. Calculate the illuminance on a small area placed at 1, 0, 0 in such a way that the normal to the area makes angle of 37 degree with the x-axis. So let's try to imagine the situation. Ninth one. So the situation is, let's say this is the x-axis and this is the y-axis. This is the origin, so source is here at the origin. Now there is something which is 1 meter away on the x-axis and its orientation is 37. Its perpendicular is in the orientation of 37 degree from the x-axis, and this is the area, some area is there. So now what do we have? We have luminous intensity 628 over 4 pi, because it is uniform in all directions, so 450 candela. R is 1 meter, distance is 1 meter, theta is 37 degrees. So illuminance, which is E, which will be equal to I cos theta over R square, 50 into cos 37 degree over R square is 1 square, that is 1. So it will give us 40 lux. E will be equal to 40 lux. Now in the 10th one, we have the illuminance of a small area changes from 900 lumen per meter square to 400 lumen per meter square when it is shifted along its normal by 10 centimeter. Assuming that it is illuminated by a point source placed on the normal, we need to find the distance between the source and the area in the original position. This is the 10th one. Situation is like this. This is the origin, A, B, 10 centimeter apart, and let's say this is x centimeter. So first of all, what we have for A, illuminance is 900 lumen per meter square, and for B it is 400 lumen per meter square. Now EA is equal to, we know that I cos theta over x square, distance square, and EB will be equal to I cos theta. Here it will be x plus 10 whole square, because its distance from origin is x plus 10. So now I will be EA x square over cos theta, and I equal to EB x plus 10 whole square over cos theta. So we can equate the two equations. Cos theta will get cancelled out, it will remain like this. We can take the ratio as well if we want. So ultimately what we will have, 900 x square equal to 400 x plus 10 whole square. So x over x plus 10 equal to 2 by 3. So from this x will come out to be 20 centimeters. So the distance is 20 centimeter of A from the origin, and B is 30. Okay, B is 20 plus 10, that is 30. Okay, 20 plus 10, 30. So for A only 10, for B 10 plus 20, that is 30. In the 11th one, we have a point source emitting light uniformly in all direction. It is placed 60 centimeter above a tabletop. Now illuminance at a point on the tabletop directly below the source is given, which is 15 lux. So we need to find the illuminance at a point on the tabletop 80 centimeter away from the first point. So this one is the 11th one. So the situation is like this. let's say this is theta, this is 0.8 meter, A, B, let's say this is O, this is 0.6 meter, this is 1 meter. So given lux for EA is 15 lux, I naught over 60 square, I naught equal to 15 into 0.6 square, because 60 centimeter was there, so we put 0.6 meters. So now let me write this also so that you do not get confused. It will come out to be 5.4 candela. Now EB will be equal to I naught cos theta over OB square, so which will be 5.4 into 3 by 5 over 1 square. So from here EB will come out to be 3.24 lux. What is 12th one? In 12th one we have light from a point source falls on small area placed perpendicular to incident light. Now if the area is rotated about the incident light by an angle of 60 degree, what fraction of illuminance will change? So the important thing is that it is a point source. So point source emits light uniformly in all directions. So it will not do anything, it will not change the illuminance. So the illuminance will not change, it will remain same even after we rotate the area by 60 degree. Now let's start the 13th one. So in the 13th question, there is a student studying a book placed near the edge of a circular table of radius r. A point source of light is suspended directly above the center of the table. Now what should be the height of the source above the table so as to produce maximum illuminance at the position of the book? So 13th one. So the situation is like this, there is a point source here, okay. Now this is the table, this is the radius of the table, this is the height, this is, let's say this is small r, this is the angle, and this is our table. So E equal to I naught cos square cos theta over r square. So we will have I naught h over r cube, because cos theta is equal to h over r. Now it will give us I naught h in over r square, h square 3 by 2, sorry, capital R, okay. Why? Because r square is the hypotenuse, it will be r square plus h square, so r will be equal to root r square plus h square. So we will have this thing here. Now after this, for maxima, so for maxima d by dh should be equal to 0. So it will be like I naught, now we need to differentiate. So we need to differentiate using the division rule. So it will give us this value plus h square 3 by 2 into 2h. Now over r square plus h square whole cube. So it is all equal to 0. So after solving this you will get like this. So h will be equal to r over root 2. So this is how you can solve this question.